So this section will be focused on robot perception. Let's first understand what the term robot perception is. So as humans, we use different parts of our body to get an understanding of the environment that we are in. So robots also need to do that. It needs to have some understanding of the environment it is currently in before executing its navigational and manipulation tasks. How the robot does that is it uses different sensors to achieve this task. And there is something called the action perception loop common to a lot of robotic applications. So in that, what happens first is the sensing or perception in which the robot uses different sensors to obtain some input which actually describes the environment. And the next part would be the cognition or the thinking part. And all robots have some kind of processor to do that, to decide on the sensor input. I mean, based on the sensor input, it will decide its best course of action. And then what happens is using its actuators, it will follow that. So these three steps actually happens in a loop or a cycle. So after executing action, it will perceive again. So this is called the action perception loop. And talking about the perception, a robotic application would use different kind of sensors to gain some understanding about the environment. So for example, this humanoid kind of robot, it has different parts. Like it also has the cognition part, the cohesion processor, and it also have actuators, the motors and arms. But what we are more interested in the perception are the sensors. As the sensors, it has two fisheye cameras, and it has a laser scanner, and it has initial measurement unit, and it has a pressure sensor. It has a torque sensor, so different kind of sensors. But there will be some other sensors in different robotic applications, such as ultrasonic sensors, infrared sensors, different type of cameras, RGB sensors, depth sensors, things like that as well. And the perception not just means obtaining the sensory input data. There will be some algorithms running on top of that data to actually perceive the environment well. Because if you take a camera type of sensor, it will give us a video stream, right? But the raw video stream does not make much sense to a robotic application. What it does need to is that it should process that video frame in a way it understands what are the objects around it, stuff like that. I mean, any sensor input in its raw form might not be very useful. There should be algorithms built on top of that to gain some intuitions or like a deep understanding from that sensory data. So I will talk, for each kind of sensor like this happens, but I will mostly focus on camera and vision aspects of it. Some of the robot vision applications could include object detection, object recognition, object tracking, face recognition, force estimation, and collision avoidance and robot navigation. So each of these tasks, they try to do something out of the input video stream that they get. So, for example, object detection means it tries to identify different objects present in that video frame. Object tracking means going one step further, and with time, it will try to not just detect the objects, but track objects, how they move from each frame to the other frame. So collision avoidance again an important aspect for a robot to stop hitting obstacles around them. Another important example when we talk about perception is a self-driving car, which is like a very hot topic through the last decade. So in autonomous driving or self-driving, we want to carefully maneuver vehicle through the roads, and roads can be quite complex environments, right? There can be people, houses, vehicles, different stuff around the moving vehicle. So it should perception is very important. So it should identify the environment, and it can use vision-based cameras and LiDAR, laser detection and ranging sensors, and GPS, and there can be other ultrasonic and other radar sensors. Like there can be different sensors that a self-driving vehicle would use to obtain sensory input for the for like process them and get some understanding about the environment. So like the image on the or the GIF on the left shows the point cloud data around the driving vehicle, which it would like mostly used to identify. Yeah, so I was talking about machine learning and deep learning. This refers to networks or models that are trained to do specific tasks. So traditionally, before that, we had algorithms where we like instruct step by step what it should do. But in machine learning and deep learning, we do not tell the model or the algorithm to do to like we don't instruct them specifically to do these tasks, but what we would give is like a set of inputs and a set of labeled or annotated outputs. So based on those inputs and outputs, the networks actually learns what its task is, and they are trained to do that task. And then we can use the trained models or the networks on new inputs so that the output would be generated. So in machine learning, the feature extraction part is usually done separately, but in deep learning, that is also included in the model itself. So moving on to the next slide. There are some computer vision and deep learning based technologies that we use to perform the aforementioned tasks, such as like object detection, tracking, face recognition, and so on. So this OpenCV is a library which supports a lot of image formatting and feature detection, and even like it has support to neural networks and stuff as well. And the other PyTorch, Cafe, TensorFlow, Keras, they are all like deep learning based frameworks where you can train machine learning or deep learning models for specific tasks. Now actually we come to the interesting part. So how robot operating system ROS supports these perception kind of tasks. The ROS has inbuilt support to OpenCV. It has a ROS package called Vision OpenCV. So we can use that directly to perform some useful image processing and computer vision related applications. So the earlier deep learning platforms like the TensorFlow, Keras, and PyTorch, they are based on Python, and Cafe is based on C++. So those are like different libraries, right? I mean, we can use PyTorch or TensorFlow to for our own tasks separately without ROS. But what's interesting is since those are written in Python and C++, and ROS supports Python and C++, we can integrate those to ROS. So the earlier final year project video that I showed, that's what we have exactly done. We have developed the deep learning based detection framework separately, but we use ROS to integrate them, which would be more useful in a connected kind of thing. And the other important thing is like cameras, LiDARs, and there are like many sensors that we use in robotic applications. And those lot of, I mean, almost all of them, almost all of commercially available sensors and other camera LiDARs and stuff, they have built-in support with ROS, and they have ROS packages which would allow us to get their sensor information, as well as we can issue commands to control those sensors as well, and they usually have specialized ROS message types as well. And if those packages are not available, one can develop as well, but for almost all of the commercially available sensors, they have built-in support with ROS. And let's move into some examples of perception tasks done with ROS. And this is a pick and place robot, and what it does is like it would try to identify the objects in front of that and put it into two different bins. So for doing that, what the methodology is, it uses training and the data collection part is there. So it will gather different kind of objects, and then this Hogan surface normal feature extraction step is done to identify different features in those objects. Features can be things like edges, corners, and blobs kind of stuff. And on top of those features, SVM or supported machine classifies strain, and this strain classifier then can then be used to identify new objects. And that is happening in the inference part. The RGB depth point cloud is taken, and some pre-processing techniques such as filters, downsampling, and clustering algorithms are applied. Then the features are extracted again, and when those are sent through the trained SVM classifier, the class would be identified, and based on the class, the robot can actuate its arms and put the right object in the right bin. And this is another application with deep reinforcement learning to pick up object. So reinforcement learning is again an interesting learning algorithm that has emerged in the last few years. So in reinforcement learning, what we do is like we learn by doing. So the RL agent, reinforcement learning agent, will execute different kind of things, and we usually have a reward function which will tell whether its action was in the correct direction or in the wrong direction. So based on that, what happens is it will improve continuously from time to time. It will train better and better, and it will become doing the intended task with time. And actually, you might have heard there are some RL-based algorithms that could outperform humans in some games, such as Go. And here in this application, what we are focused is like a picking up object, and we have used deep reinforcement learning together with ROS to achieve that. And rather than instructing the robot to how to pick a object like without hard coding the commands like do this without instructing the robot to do that, what we have done is like a reinforcement learning based approach. So in that, what happens is it will try to pick the object first. It might fail, but with time it will improve what to do, how to pick object, and at the end it will perform better and better. And there was like interesting application in one of exhibitions organized in our department. In that, there was like a line following task, again done with deep reinforcement learning. So in that also, the robot improves from time to time, and at the end, it will go very smoothly on the line. Let's look at some videos as well. So this is object recognition example done together with ROS. So this is like not machine learning or deep learning based approach, but traditional approach. So what happens is like in the 2D image that is captured, there is algorithms to detect features. So the features can be edges, corners, blobs, kind of stuff. So they are like marked in yellow. So those features are identified. And then what happens is it will create a template out of these features. So, I mean, human, we do that, like we cover the image area containing the Coca-Cola can, and then it will create a feature template. So then we can match the feature templates with the image, and based on the matching, it will be able to detect Coca-Cola cans in different kind of images. Let's move to the next video, which is on face recognition example. So this is also done with ROS to an algorithm to identify different phases. So you can see the phase is detected and annotated with the name of the person in this example. So both of these examples, the last two videos are taken from Construct-Sim. So that is the exact platform that we are using for hands-on tutorials as well. So they have this course on perception, which covers this. I mean, including this too, it has like a lot of resources, and the codes also you can have a look at how those are performed. So if you are interested in perception along with the robot operating system, I recommend that you go through that course and follow their tutorials and stuff, and you would gain a lot of understanding. So the important thing to note is like these kind of application object detection, face recognition. Like I'm sure like most of, I mean, at least some of you are familiar with this type of, at least they have seen different videos and stuff. But the important thing that I'm trying to explain to this presentation is a lot of these things can be integrated with ROS. And by doing so, we have a way to easily implement this kind of algorithms in robotic kind of application, because like ROS acts as interconnector between sensors, actuators, and the controlling processor. So together with ROS, it would be like more powerful, and the algorithms work well, and we could develop a very interesting application. So that actually brings us to the end of this presentation. Back to you.